All right, let's dive straight in. You're watching AI Paper Podcasts, and today we're looking at a really interesting paper, PLM Perception Language Model for Video Understanding from Scratch.
Yeah, this one caught my eye too.
Have you ever felt like, AI video understanding just kind of scratches the surface?
Totally, like basic action recognition, person walking, that kind of thing.
Exactly, but this paper, PLM, it goes way deeper. Imagine asking an AI, okay, how exactly is that person holding the sandpaper?
Right. Not just that they're sanding, but the grip, the pressure maybe.
Precisely. And getting an answer like firmly with their right hand, between the right thumb on one side, fingers on the other side, that's the kind of detail we're discussing.
And that's the gap the PLM team wanted to fill. They saw vision language models, VLMs, getting great at images, but video often relied on these huge proprietary pre-trained models.
So they decided to build their own.
Exactly. Build a powerful video VLM, PLM, from the ground up. And importantly, do it openly and reproducibly.
Okay, so open source is key here.
Very much so. And maybe even more impressive, they created these massive new data sets, the biggest collection actually of manually annotated fine-grained activity Q&A. That's PLM FGQA.
Fine-grained Q&A.
Yeah, questions about how actions are done. And also PLM STC, which is spatio-temporal captioning descriptions tied to when and where things happen in the video.
Wow, how much data are we talking?
Get this, 2.8 million instances combined. Really detailed stuff, movement direction, object states, locations, the whole 9 yards.
2.8 million, that's huge.
It really is. And to test models on this kind of detailed understanding, they also built a new benchmark suite, PLM Video Bench.
A dedicated benchmark. Makes sense.
And spoiler, their PLM models perform really well on it. So for anyone listening, especially AI researchers, ML engineers working on video, this is a significant paper. Open models, massive detailed data, new ways to evaluate. It's pretty exciting stuff.
Okay, great overview. So let's get into the nuts and bolts, this PLM model, what's under the hood, what's the architecture look like?
Okay, so at its core, PLM connects a pre-trained vision encoder. They use the perception encoder, or PE, with a Llama 3 language decoder.
Llama 3, okay. Familiar territory there.
Right, so you've got the PE acting as the eyes, Llama 3 as the brain, if you will. And linking them is a pretty simple two-layer MLP projector. Think of it as the translator between the visual world and the language world.
A translator, got it. And do they use the same setup for all model sizes?
They scale it. So for the smaller PLM models, the 1 billion and 3 billion parameter Llama 3 versions, they use the PE L14 vision encoder.
Okay.
But for the bigger 8 billion parameter model, they use the more powerful PE G14 encoder. Matches the scale.
Right, scale the eyes with the brain. So how does this setup actually, see the images and videos? You mentioned high resolution, lots of frames.
Yeah, it has to handle a lot of visual information. They use this technique called dynamic tiling.
Dynamic tiling.
Yeah, instead of trying to process one massive high-res image or video frame all at once, which can be computationally, insane, they break it down. For images, they can break it into up to 36 smaller tiles, each 448 by 448 pixels.
36 tiles.
Yeah. And then they apply 2x2 average pooling to the features from each tile to kind of summarize the important bits before feeding it to the language model.
Okay, so process smaller chunks, then summarize. What about video?
Similar idea for video. They process 32 frames, also at 448 by 448 resolution, and apply that same pooling strategy to each frame's features. It lets the model focus on details within each part or each moment in time.
That makes sense. It's like managing complexity by breaking it down. Okay, so that's the architecture. How do they actually train this thing to get that deep understanding? It sounds like a complex process.
It is. They use a carefully designed 3-stage training process. Stage 1 is what they call Projector Warmup.
Warming up the translator.
Exactly. They keep the vision encoder and the Llama 3 model frozen. They don't update their weights yet. They only train that 2-layer MLP projector.
Okay. On what data?
On about 1 million synthetic image caption pairs. They used SA1B data with generated captions. The goal here is just to get that connection, that projector, working smoothly and stably before they start training the whole system. Uses a pretty standard setup, learning rate 1E4, batch size 64.
Right, get the connection stable first, like tuning an instrument. What's stage 2?
Stage 2 is large-scale mid-training with synthetic data. Now they unfreeze everything. The vision encoder, projector, and Llama 3 are all trained together.
Okay, the full band is playing now.
You got it. And they train it on a massive amount of synthetic data, about 64.7 million images and videos.
Whoa, 64 million, all synthetic.
Yeah, with automatically generated captions and question-answer pairs. And they increase the input complexity here too, using up to 16 tiles or frames.
What kind of synthetic data? Just natural images?
Oh no, much broader. Natural images, sure, but also charts, documents, even videos from different perspectives like first-person egocentric views and third-person exocentric views.
Diverse.
Very diverse. They mention using their internal data engine to generate all this stuff at scale. It gives the model a really broad foundation. Global batch size 2048 here, learning rate 4E5.
That synthetic data stage sounds crucial for building general capability. What's the final step? Stage 3.
Stage 3 is the Supervised Fine-Tuning, or SFT. This is where the real magic for fine-grained understanding happens.
Okay.
They train the full PLM again, but this time on about 21 million high-quality human annotated data points, images, videos, text data.
The human touch.
Precisely. And they push the model even harder here, maximum input resolution, so up to 36 tiles for images, 32 frames for video, and longer sequences overall. Batch size 124, learning rates depend a bit on the model size.
So this SFT stage is where it learns the nuances.
Exactly. That meticulously labeled human data allows the model to grasp the complex, subtle details needed for those really challenging video understanding tasks we talked about earlier. The paper's Table 1 actually lays out these 3 stages really clearly: the modality, data source, what gets trained, the tile frame counts for each stage. It's a good summary.
Okay, so it's this blend. Synthetic data for breadth, human data for depth. Let's talk more about that data mix. Why not just use one or the other?
Well, the paper argues, and it makes sense, that the synthetic data is great for building general visual and language capabilities. It exposes the model to just a vast range of situations, helps it learn basic connections.
Like the fundamentals.
Right. But for the really intricate stuff, understanding how actions are performed, those subtle differences, synthetic data often just doesn't capture that level of nuance. You really need humans in the loop for that.
Back to the sandpaper example. Synthetic might say sanding, human says firm grip, thumb here, fingers there.
Exactly that. The human annotation provides that crucial layer of detailed, real-world grounding that synthetic data struggles with.
Okay, so what specific data sets make up this mix? You mentioned there are huge ones, PLM, FGQA, and PLM STC.
Yeah, those are the headliners they created, totaling about 2.8 million human annotated instances. Then there's that massive 64.7 million synthetic samples pool.
Right.
And they also smartly incorporated about 5.6 million samples from existing open source image and video datasets. So it's a real curated collection. Table 2 in the paper lists out the different datasets involved.
Seems very comprehensive. And you mentioned a data engine for the synthetic stuff. What exactly does that do?
Yeah, their data engine seems specifically designed to generate synthetic data targeting key VLM skills. Things like OCR, reading text and images.
Okay.
Understanding charts, documents, generating captions for images and videos, creating relevant question-answer pairs for visual content.
How does it generate the captions and QAs?
Interestingly, they actually use Llama 3 itself for some of that generation. Appendix K touches on this, so using a powerful LLM to help create training material for another VLM, it's a clever bootstrapping approach.
Yeah, using the tool to build a tool. Okay, let's zoom in on those 2 big human annotated data sets they built. PLM, FGQA, first fine-grained question answering. What makes it so special besides the size?
It's the focus. 2.4 million QA pairs specifically about the how. How is the action done? What's the manner of movement? What's the state of the object being interacted with? What are the spatial relationships?
So really digging into the mechanics of the action.
Absolutely. And as you said, the scale is unprecedented. They mention it's about 8 times larger than the previous biggest human annotated video QA dataset. Figure 4 has some great examples showing the level of detail in the questions and answers.
Creating 2.4 million detailed, human-verified QA pairs sounds like a monumental effort. How do they actually do it?
It was definitely a sophisticated process. They described this multi-stage data engine they developed for it. First, identify interesting video segments. Then, use models, sometimes text LLMs, sometimes earlier PLM versions, to generate draft questions and answers.
Okay, initial automated pass.
Right. But then comes the critical human step. Annotators carefully reviewed, corrected, and refined those machine-generated answers to ensure they were accurate and met that high bar for detail.
Human verification and refinement. Crucial.
Absolutely. Appendix H goes into the weeds on this temporal segmentation, Q&A generation, verification, quality control. They even used LLMs to generate tricky wrong answers distractors for multiple choice questions, which humans then verified.
Wow, generating plausible wrong answers. That makes the evaluation tough.
Exactly. And they use a specific metric metric for this FGQA task called multi-binary accuracy, MBAC, which is suited for evaluating answers with multiple detailed components.
Okay, that explains FGQA. What about the other one, PLM STC? Spatio-Temporal Captioning, what does that involve?
So PLM STC has around 476,000 captions. The key here is that each caption describes an activity but is also linked to when it happens, timestamps, and where it happens using segmentation masks, they call them masklets, for the subject in each relevant frame.
Masklets, like little masks.
Yeah, basically highlighting the specific person or object doing the action within the frame. Figure 5 shows examples, so a caption might say, person A throws a ball to person B between second 3 and second 5, and the masklets would highlight person A during that time.
Ah, so it grounds the description in both space and time within the video.
Exactly. It lets the VLM associate the description with a specific actor and their location over a specific time interval. Really precise grounding.
How did they create these annotations? Another complex process.
Also quite involved, done in 2 main stages. First, annotators identified key moving objects and used the segment Anything Model, SAM, to help generate and refine these masklets frame by frame. If the object went out of frame, it got marked.
Okay, so tracking the where.
Then, a different set of annotators watched the video segment focusing only on the masked subject and wrote detailed descriptions of their actions and changes over that specific time window, considering the context. Followed by more verification and quality control, of course. Appendix I has the details.
Okay, these datasets, FGQA and STC, sound incredibly valuable for pushing video understanding forward. Now, you mentioned they also built a new benchmark, PLM Video Bench, to test these kinds of skills.
That's right. Having created the data and trained the models, they needed a way to properly evaluate performance on these challenging fine-grained tasks. So they built PLM Video Bench. Figure 6 gives a nice overview of what's in it.
What kind of tests are included in this video bench?
It covers several key areas. Obviously, there's fine-grained QA using their new FGQA dataset.
Makes sense.
Then there's Smart Glasses QA, or SGQA. This focuses specifically on egocentric video first-person view, like from smart glasses.
Oh, interesting. How do they evaluate that? QA can be subjective.
Good point. For SGQA, and actually some other tasks too, they use LLM Judges. They feed the model's answer and the ground truth answer to a powerful LLM like Llama 3.370B Instruct and have it score the quality. Section C.3 even gives the prompt they use for the judge.
Using an LLM as a referee. Clever.
Yeah.
What else is in the benchmark?
There's video region captioning, PLM RCAP, where the task is to caption a specific tracked region in the video. Again, LLM judges assess the similarity of the generated caption to the ground truth.
Okay.
Then there's dense video region captioning, PLM RDCap, which is harder captioning all significant activities within a region. They adapt a metric called SOTA using the LLM judge scores for this.
Yeah, dense captioning. Okay.
And finally, region temporal localization, PLM RT lock. This tests if the model can find the exact start and end times for a specific action described in a query within a certain region. They use standard metrics for this, like mean recall based on temporal overlap.
Wow, that sounds like a really demanding set of tests. It covers detail, grounding, localization. Very thorough.
It really is. It's designed to push models beyond simple recognition towards genuine, detailed comprehension.
So the million-dollar question, how did PLM actually do on standard benchmarks first?
The results look pretty strong. Table 3 shows its performance on image benchmarks, things like captioning, general perception, reasoning, even chart and document understanding. It holds its own against other models, and they specifically checked for hallucination, which is important.
Good, checking for reliability. And on video benchmarks.
Similarly positive results there, shown in Table 4. Across tasks like standard video captioning, short and long video QA, and existing fine-grained QA tests, PLM performs very competitively, often beating other open access models and sometimes getting close to proprietary ones.
Okay, competitive on existing tasks. But the real test is their own benchmark, right?
Yeah.
PLM Video Bench, designed for these new fine-grained skills.
Exactly. And that's where PLM really shines. Table 5 presents the results on PLM Video Bench. It clearly shows that the model, trained with their methodology and those detailed data sets, excels at these fine-grained QA and spatio-temporal reasoning tasks.
So the specialized training paid off on the specialized tests.
It seems so. They also did an ablation study, Table 6, where they trained models with different parts of their data mix removed. That really helps pinpoint which data components contribute most to which capabilities. Very useful analysis.
Ablations are always insightful. Did they show any visual examples of what the model can do? Sometimes seeing is believing.
Oh, yeah, definitely. The appendix, figures F5 through F10, is full of qualitative examples. You can see it doing OCR pretty well, answering complex questions about images, like in figure F8, there's an oven image, and it correctly identifies what's inside, the temperature setting. Figure F9 has a great caption generated for a complex city skyline image. And figure F10 shows examples of the video region captioning and temporal grounding, pinpointing actions in space and time. These examples really help visualize the kind of granular understanding PLM achieves.
It's great to see those concrete examples. Now, no research is perfect. Did the authors talk about any limitations or where they see this going next?
They did. Section 7 discusses limitations, which is good scientific practice, provides a balanced view. And they also point towards several interesting directions for future work building on this foundation.
Good. And just to circle back on a point you made early on, the reproducibility aspect. They really emphasize that.
Hugely. It seems like a core principle of this work. They stressed creating reproducible training pipelines, using public data where possible, and crucially, they're releasing their PLM models and those massive PLM FGQA and PLM STC datasets.
That's fantastic for the research community.
Absolutely. It lowers the barrier to entry for others wanting to work on detailed video understanding and allows the whole field to build on their progress much faster. It's a really commendable approach.
So if we were to boil this down, what are the main takeaways for our audience from this deep dive into PLM?
Okay, key things. First, PLM is a new family of strong, open-source vision language models built from scratch specifically for video understanding. Second, a massive contribution is their creation of PLM FGQA and PLM STC, the largest, most detailed human annotated datasets for fine-grained video Q&A and spatio-temporal captioning. Third, they introduced PLM Video Bench, a new benchmark tailored to evaluate these advanced capabilities. And fourth, their models show really strong performance, especially on tasks needing that deep, granular understanding.
Why should our audience, the AI researchers, the ML engineers tuning in, really care about this particular paper? What's the significance?
Well, it marks a real step change in the level of detail we can expect from video understanding AI. Training from scratch with this kind of meticulously annotated data clearly works for achieving fine-grained analysis. The open models and data are huge enablers for further research and development. Think about the potential applications.
Like what?
Like AI coaching systems that can give specific feedback on how you're performing a physical task, or assistive AI that truly understands complex procedures shown in video. Much better video search and analysis, grounded video transcription that knows who did what, when, and where. It just unlocks a much deeper interaction with video content.
That really does open up a lot of possibilities. Okay, let's leave our viewers and listeners on AI Paper Podcast with a final thought then.
Sounds good.
Considering this jump in detailed video understanding, think about your own work, your own applications. What new possibilities emerge when AI can answer not just what is happening, but the intricate how, when, and where within a video? What new questions can you ask? And maybe just as importantly, how will open, large-scale, detailed datasets like PLM FGQA and PLM STC shape the future progress of this field? Definitely some interesting things to ponder.